So this is a reversible reaction problem, and we will determine the solution of that based on the principles that were covered in the presentation of the first order and the second order reversible reaction. So you're given here the reversible gas phase decomposition of nitrogen tetroxide or N2O4 to nitrogen dioxide, NO2. So if you could see in here, the coefficient of nitrogen tetroxide is just 1, but on the other side it's 2. So it will not be falling in any of the specific cases of reversible reactions that we have discussed. Now for this problem, it is carried out at constant temperature. So your feed consists of pure dinitrogen tetroxide at 340 Kelvin and 202.6 kilopascal. Now the equilibrium constant is at 340 Kelvin given at a value of 0.1 mole per decimeter cube. Now you are to calculate the equilibrium conversion of dinitrogen tetroxide in a constant volume batch reactor. In this problem class, there was really a mention that your reaction is carried out in a constant volume batch reactor. There is a necessity for that being mentioned because you are given a gaseous reaction. A gaseous reaction oftentimes class is variable volume in nature. So if the problem did not specify this condition of constant volume batch reactor, you are not allowed to use any of the formulas that we have discussed so far concerning constant volume batch reactor interpretation of data. So you will be discussing in a few minutes the formula for variable volume reactions. Okay, so in here it was really specified that it's constant volume, so we're okay. We can use the principles and formulas, if applicable, that we have discussed so far because this is a constant volume batch reactor problem. Okay, so let me clear first markings here, and we'll go to the Jamboard. That way I will have more space to write on the solution. So let me just take a picture of this problem. Okay, now we go to our Jamboard. But do you have any questions so far as to what we have discussed yesterday? It's none. We'll share. Now, so of course, we're going to write with the given information. Reversible decomposition of dinitrogen tetroxide. So we'll have this one. This is the stoichiometric equation provided. And you will have 2 moles of nitrogen oxide produced in this reversible decomposition. You have K1 here for the rate constant in the forward reaction, and K2 for that in the reverse reaction. This is carried out at constant temperature. Now, the feed consists of pure dinitrogen tetroxide, so meaning it does not have any contaminants, and there is no initial amount of products present. So there's no product present initially. We only have everything in terms of dinitrogen tetroxide. Now, the temperature in which the reaction was carried out is 340 Kelvin, and the pressure is at 202.6 kilopascal. Now you're given the equilibrium constant, and it's at 0.1 mole per decimeter cube. Okay, so we are required to determine the equilibrium conversion. Okay, the equilibrium conversion of nitrogen tetroxide at a constant in a constant volume batch reactor. So if it's a constant volume batch reactor, V is also a constant. Okay. So we're starting with we are given rather a problem wherein we cannot apply any of the pre-derived formulas for reversible reaction. So if you are the one solving this problem and you are given this information, what do you think will be the first step that you will most likely perform or do in this case? You are given the stoichiometric equation, you're given the temperature, the pressure, and the equilibrium constant. How will you solve this problem if I may ask you? How will you solve the problem? Any suggestion? Anybody? How will you start solving the problem? How will you start solving the problem? Nobody? Nobody knows how to start? How do we start in the first place deriving the uh, formulas for the first order reversible reaction and second order reversible reaction? Just give me an idea that you have an idea on what you're going to do in here based on what you have learned yesterday. What will you do? Okay, if I will ask you Drexel, what will you do? Drexel, what will you do? Or Aina, what will you do in this case? You are after the equilibrium conversion. Think, based on what we have discussed yesterday. Are you there? Am I alone here?
Miss, ano to din, miss, ang question?
How will you start solving this problem? What will you do first? Or Patrick, you have to train your mind plus to critically think. You have to think that it's not actually it's not 100% it's 100% you will not be given a formula that you can directly solve, you can use. The formula will guide you on how to write your own formula that is suitable for a given problem in kinetics. It's very seldom that you'll be given exactly the same formula to use for a given condition. I'm thankful that I have one here in the inbox. Rate equation, miss. Okay, I will write the rate equation. Will that help because I need the equilibrium conversion? If I will write the rate equation, will that help because I need the equilibrium condition? Find the concentration. I will find the concentration. What concentration will I find, Dexel? What concentration will I find? The N2O4, miss. How will I find it then? If I'm going to ask you, how will I find it? When you work a problem in kinetics, you always associate your steps or your procedures based on the given information. So you are given the equilibrium constant, you're given the temperature, the pressure, and the stoichiometric equation. So based on your given information, meaning you're going to use the given information, what will you do? Okay. To save us some time, you are given the equilibrium constant. Okay, hopefully this one is right already. Vincent Villares, equilibrium expression is correct. Vincent, correct. You are to write the equilibrium expression. You are to write the equilibrium expression. So you write Q sub C is equal to, we'll have 0.1, and this is to be equated to what? Based on what you have learned yesterday. The equilibrium constant will be equated to, what should I use here? What will I equate it with? Hmm? Okay. If you're going to equate it with k sub 1 and k sub 2, you're not given both. You will create another problem for yourselves. Thank you, John, Albert Villarosa. Very good. And Johan, you are to equate, or you have to write your equilibrium expression based on the equilibrium concentrations. Okay? The equilibrium concentrations of the species that appear in your reversible reaction. So how is that going to be? So let's say we'll have this as, use a different color. So let's say this is B and this is A. Okay, so I will write now my equilibrium expression. So it should be CBE squared because of this 2 here over, say, CAE. Now, what then would I do? I will have CBO 1. B is being produced, so it should be plus XBE divided by CAO 1 minus XAE. Now, this is squared, so this has to be squared, and this has to be squared. Okay? Then we will simplify further. So you have 0.1 being equal to, have this one. You have to expand this and distribute this. So in the process, you will have CBO squared if it's 1. In the middle, this will be 2XBE. And you're going to multiply it with this. So you will have 2 CBO squared X sub BE. Okay? Because the product of these two is 2X sub BE. Now, the last term will be the square of this multiplied to this. So I can write it as CBO squared XBE squared. The denominator is CAO minus CAO XAE. Okay? Now, based on stoichiometry, what do you have then? Do you have CBO initially present? Or based in the given problem, do you have CBO initially present? Aina. Do you have CBO initially present, Aina? Or do you have B initially present?
Yes, yes.
What about you, to Yuhan. Do we have B initially present?
I think Miss wala, Miss.
Why? Why do you think we don't have B initially present? Product B, and that is our nitrogen dioxide. Okay, so if you were listening to the problem, it was read a few minutes ago. It said that we're starting with pure. I even emphasize it, dinitrogen tetroxide. So there's no B initially present. So this must be 0. Okay. Now this CPOXBE, this one, the CBOXBE can be expressed in terms of CaOXAE based on the stoichiometry. If we go to the next slide, your CaOXAE over 1 is equal to CBOXBE over 2. Why is that? It's because of this stoichiometric coefficients 2 and 1 that you see in your reversible reaction. So now you can express the CBOXBE both squared here in terms of CaOXAE. You may wonder why the need to do that, Miss Ali, because you're after XAE. You don't want XBE. So, by the way, before we simplify this further, since this one is already 0, the initial concentration, we can have this as well as 0. So what is left here will be the CBOXBE quantity squared changed to CaOXAE. So we can place here CBOXBE is equal to 2 CaOXAE. Okay? So we go back to our given, that's 0.1, and we have the numerator now. This being 0, so you have this now changed to CaOXAE. So twice of CaOXAE, this is to be squared, because what you have here is squared. Now in the denominator, you have CaO. I don't want to have it expanded because it will not help. I'll write it like this again. But you can have it there as written as CaO minus CaOXAE. But that will have, we will have to substitute later a value that will lengthen the procedure. But you can write it that way or this way. No, it doesn't matter. Now in here, you can cancel the CaO. The purpose of me writing it this way is for me to cancel the CaO here and one of the CaO on top. So I will have 0.1 equal to, so what you have left here is 4 CaO XAE squared, and you have 1 minus XAE here. Now our goal is to determine XAE. The equilibrium conversion, the equilibrium conversion for A, our dinitrogen tetroxide. But I need the CaO. How do I find the CaO? Okay, if this is our equation 1, I need CaO. That way, the only unknown left here is XAE. How do I find CaO? Vincent, do you have any idea? How do I find the CaO? Or Via, how do I find the CaO? This is my given. How do I find the CaO? Vincent. Okay, somebody wrote here. Via. P over RT. Very good, Via. So you're going to find the concentration based on the pressure provided. You will use this total, the pressure of the system, because initially your system has only dinitrogen tetroxide. So this pressure here is entirely due to the presence of the sole species at the start of the reaction, which is 202.6 kilopascal. So we're going to do that. So if you're going to use the ideal gas equation, assume ideal behavior, you will have P over RT, as what Bea said, is N over V, which is equal to the concentration. So if you'll find XaO, the initial concentration of A, we're going to use the PaO over RT formula. So we have 202.6 kilopascal. And we have 340 for the temperature. So I'll place here 340 Kelvin for the temperature. Now, what should be the R, appropriate R that I will use here, since I have Kelvin and Pascal for my temperature? Or you can have this converted with demand. So you will have 101.325 kilopascal equal to 1 atmosphere. So you can use the commonly used R, which is 0.08205 liter ATM per mole per Kelvin. Now, okay, now we'll have kilopascal cancelled, we have the ATM cancelled, we have the Kelvin cancelled. So the remaining unit will be mole per liter for our initial concentration. So can you please solve for the initial concentration? Okay, we have you have 0.0716. Kindly check. So if the value is okay, then 0.0716 mole per liter. Thank you, Jan, or Rexel rather. So we have the CaO. We can go back here and substitute. We have 0.1 equal to 0. We'll substitute the value of CaO. So we'll have here 4 and the CaO. And we have here XAE squared over 1 minus XAE. Alright, so you'll be able to solve for the XAE. Okay, what's the XAE? You will be getting two values because this will be a quadratic equation, but of course the other value will not be acceptable. There's always validation. This is one example. Cannot accept the negative value because we don't have a negative conversion. XAE, we have 0.04416. So this is our equilibrium conversion. 0.4416. 4416. Okay. Sige. So this is our answer. The equilibrium conversion is 0.4416. If we will extend the time class, for example, until time infinity, what do you think will be the degree of conversion of A? Let's say the problem will ask, what is the conversion of A after a very long time? What should be your answer? Like infinity is interpreted as after a very long time, or the phrase after a very long time is equivalent to infinity. How will you answer? Problem, let's say, asks, what would be the conversion of A after a very long time? What should be your answer? 1, 0.1, 0.08211. What about the others? Let me see. Who's the smartest of them all? Okay, can you write your answer there? I'll give you the answer. After a very long time, what will be the conversion of A? O, ang maisog lang niya si Albert, si Drexel. Ang iba hindi na. Pagsilin ko, who's the smartest of them all? Write your answer. We'll see. Direct message only if you don't want it broadcasted to everybody. What do you think will be the degree of conversion after a very long time for A? 1. 1. Oh, 0.1 dili. 0.1. Is it 0.1 or 1? 0.1. 1. 1, 1. 1, 1. Nagayuhom ako sa inyo, ah. Wala gid ko gali nag-sink in ang discussion regarding equilibrium. Or ang discussion sa inyo teachers ang una in terms of equilibrium. What's equilibrium? What does equilibrium in the first place represent? When a system is in equilibrium, does it mean to say that the reactions already stopped? At equilibrium, did the reaction already stop? Yes or no? At equilibrium, did the reaction already stop? Yes. What about the others? Si Vincent lang ang maisog magsabat sang yes. It will not take more than 1 second for you to type yes or no. Oh, Aina. What about the others? No. Johan is still questioning no. Yes man ako, miss. No, yes. So my question was, in the condition of, or at the condition of equilibrium, did the reaction stop already? The following, okay, di na lang gani ko maghambal ni. So, 1, 1, 2, 1, 2, 2, 3, 4. Okay. At equilibrium, the reaction never stopped. It's a continuing reaction because it's reversible. It did not stop. It's just that what is equilibrium? It's a state of balance. So when we speak of state of balance, meaning the rate of the forward reaction is equal to the rate of the reverse reaction. So it has something to do with my question a while ago that after a very long time, what would be the degree of conversion of A? So what do you think will be the answer if the reactions never really stopped. I'm referring to the forward and the reverse reaction. What is then the conversion of A after a very long time? Because it did not stop. The reactions are still ongoing. It's just that the rates are equal for the forward and the reverse reaction. So in terms of the degree of conversion of A, as t approaches infinity or after a very long time, your degree of conversion should be one last chance. What should be the degree of conversion? If after a very long time, your system already reached a state of equilibrium, the rates of the forward and reverse reactions are already equal, what would then be the degree of conversion of A? I go back to my question. So I gave you the reasoning behind how is it connected to the concept of equilibrium. What is then the degree of conversion of A after a very long time? I have two answers so far, infinity and 0. The others then, before it's 1. Now they change it to 0. What is the degree of conversion after a very long time of A? Okay. After a very long time, class, the degree of conversion of A is this. Because that's the degree of conversion at equilibrium. Even if you extend the time of reaction for dinitrogen tetraoxide to form nitrogen dioxide, after it has reached this particular condition of equilibrium, this will be your maximum degree of conversion of A. No amount of time will increase this degree of conversion because this is already equilibrium conversion. So after a very long time, A will have a degree of conversion equal to the conversion at equilibrium. Very good, Pia. So that's it. Your XAE is 0.4416. After a very long time, your degree of conversion is 0.4416. Okay? Sige. Got it. Crazy subject. Crazy subject. It will really make you think. In class, it will really make you think. I always say to my students, why is it I love kinetics? Because it's never procedural. It will always make you think. Not even unit operations is comparable to the way kinetics will make you think. Kung si Levenspiel pa, kinetics sets you apart from the other fields of engineering. Meaning, in terms of conversion of material, you have kinetics. In terms of the design of the equipments, you have equipment design and your unit operations. But the very heart of the conversion of raw material to desired product is really kinetics. So brace yourself because you will really go crazy with kinetics, as what your classmate has said there. You have to think always outside of the box. Okay? Wala kaso Miss Kislow, because as long as you do the as long as you progress, there's no problem with that. The problem is you don't make any progress at all. You have to start somewhere, and probably I don't know if some of you would agree that this subject will make you think in a far higher degree of thinking than the other subjects that you have so far encountered. It will not always give you a scenario. Unit operations will always give you a scenario wherein a particular formula could be used right away. But kinetics is different. Once one particular number is changed there, everything is changed. I'm referring to the coefficients especially. I'm referring to the stoichiometric equation. I just changed that. You will use the principle that I have covered, that I have discussed to you, but you will not use the same formula. You will have to derive your own. So that's how, again, very important your differential equation is. Okay? Now, so that's it. That's the degree of conversion at equilibrium. And that's the maximum degree of conversion for A. Now, we will continue where we ended in our slides. Now, there is this what we call reactions of shifting order. How will the order of a particular reaction, especially non-elementary, be shifted when a particular concentration dominates another? A concentration of a species in which that particular rate of reaction is dependent on. So the example is in here. So there will be several rate expressions that will be given you, in which you will be asked how will be the rate of reaction affected when one particular concentration is very high compared to another. So there are two scenarios in here, okay, just to show to you how the order of reaction shifts. Now, at high concentration of A, so that's C sub A, the reaction is zero order with rate constant equal to K sub 1 over K sub 2. Now, how is that? If C sub A is very high, it's just like in your denominator, you don't have the 1 existing anymore. It's just like out of the picture already. Why? Because 1 is very small compared to a C sub A, which could be very high. So its presence there is negligible. So we might as well write K sub 2 C sub A in the denominator. In the process class, you cancel the concentrations of A in the numerator and in the denominator, giving you a rate expression which is not dependent on any concentration, especially on A because it has very high concentration. But this time your reaction is zero order and is only dependent on the values of the rate constants K sub 1 and K sub 2. Okay, this time the stoichiometry is immaterial because you will simply be given a rate and then you will be asked questions what will happen to the rate if this one is very high, if this one is very low. So the same principle you will use as the one that I'm illustrating here. Okay, now what about if it's the other way around? You have very low C sub A. If this is very low, then this time we could say that this term is very negligible compared to 1 because your initial concentration is very low. Then your denominator is 1, giving you a reaction which is simply K sub 1 C sub A. So if it's K sub 1 C sub A, then your reaction is said to be first order with respect to A and is dependent on the rate constant K sub 1 only. So K sub 2 is not anymore a factor that will affect your rate of reaction. You get it? So that's how reaction shifts order whenever a particular concentration dominates another or whenever one's concentration is negligible compared to another. Do you have any questions? Now, let me just close this because I cannot go down. Now, I will end our meeting today with differential analysis. We will not anymore discuss this because this one is purely graphical and you will not be using this in the board exam. But on how to use this one, I suggest that if you have the soft copy of Levenspiel, you read the sample problem on differential analysis. I will try in 5 to 7 minutes to discuss how you're supposed to use the differential analysis and when. Number 1 is when do you use differential analysis. All the bulk of information that I've given you in terms of interpretation of batch reactor data is all about integral analysis. Why integral analysis? Because we're using integral calculus in evaluating the differential equations. Now, it's however very limiting, though we already have a bulk of formulas to use, because it could only be used if the set of empirical data is not voluminous. or the empirical data that is given to you to be interpreted is just small. Like probably small would be like 8 to 10, maximum 8 to 10 pair of data. That would still be okay. What about if you already have 20, 25 pairs of data, empirical data to interpret? That way you come up with the rate law appropriate for your given reaction. Then you don't use integral analysis, because if you're going to use it, then if you have to test even in the empirical method of determining the N and K, it will take you a lot of time in solving all the data that will conform to the assumed value of N that you have. Now, in determining the K value, that should not vary, because as we have discussed, the K should not vary based on the assumed value of N. I'm talking about the empirical rate equation. It would even be more difficult and cumbersome if you will use the guess and test, because in the case of the guessing and the testing, you will only use integral values of N. What do I mean with integral values of N? Whole number. So what about if your N is already a fraction? More importantly, what about if your N is a negative fraction or decimal? The guessing and the testing process will not work. But they are very useful. The integral method of giving you the formula to use is very useful if the problem already gave you the order of the reaction. So you can go directly to the formulas as presented to you during the illustration for the use of sample problems. Now, what about this procedure in differential analysis? You are given most of the time, class, a pair of data. And that pair of data always comes in the form of concentration and time. So you will be given a lot of CA here value with respect to time. So probably 20 or 25 sets of this CAT pair of data. So the first thing that you're going to do is you plot the CA versus T data. As in, you just plot. So this would correspond to points. And when you plot, let me just clear. When you plot, what you do is you have here the T, and you have here the C sub A. So you plot your data like that. So of course, your data will be scattered. Now, from that plot of yours by eye, so that's the phrase that was used by the author. By eye, draw a smooth curve to represent the data. The curve need not pass through all the experimental points. So based on the data that you have plotted, you plot the best fit curve. You have to draw it by hand. It does not have to pass all your data points, but you have to draw it just the same. So by hand, for example, this is just how will I do it. Depends on the one who's drawing the best fit curve. So probably I'll do mine like that. So I did not pass these points here, but almost I touched this point here. Okay, this one, but this one did not. So that's my best fit curve. Now, since you already have done the best fit curve, you go to step 3. Define the slope. So what is the slope of this particular curve? It depends on the location of the point or the location on the curve in which you want to determine the slope. Because we know for one that the slope for this curve will be varying because it's a curve, it's not a line. So determine the slope. That would be the dCA dt, or specifically the negative dCA dt, or the negative R sub A, if A is your reactant of the curve at selected concentration value. So in my case, I have that. And what I'll do, I'll use a different font here, color here. On the points that I have passed through, I'd like to select those. So this point I almost passed through, so I will select this point also. And let's say I have another one here which I did not pass, but I will select it just the same. And another here. So you're the one who's going to select these points. And what you do, you draw a tangential line on the curve passing through these points that you have identified or chosen. So this one, I have one here, So it has only to touch the curve in that particular point. What's the association of these lines? That's these tangential lines on your chosen points on the curve. You will determine the slope of these lines. The slope of this line is your DCA dt. Okay, the slope of this line. So for corresponding, so you will have a new table now, class. You'll have a new table. For a particular CA value, the CA value in blue, because you have chosen that, so you just read the CA values here. So let's say in our case, we have 4. For the CA values, you will write down the slope. The slope, which is the DCA dt. The DCA dt, the slope of these 4 lines. So you will have that one also. Oh, it's written here. You have CA and DCA. What will you do with the CA and DCA? You get the LN. So from these 2 sets of data that you have, draw pa ni siya, kaya pili mo ni siya. Basahon mo lang di ang concentration. You get the LN of that. So meaning you will have another table comprising the LN of CA and the LN of RA. What's the purpose of the LN of CA and the LN of RA? You need to plot them. Plot LN of CA versus LN of RA. The linearized nth order form of the rate law together with the equation of the best fit line will give the order of the reaction. I will make this smaller. It will give the order of the reaction and the specific reaction rate constant. Now you may ask, how could that be? How can the LN of RA and the LN of CA give me the order of the reaction and the reaction rate constant? I like to go here so I can write, okay? I will clear my markings here. That way I can write something new. So I'll go here. How will the LN of CA and RA give me the order of the reaction? Remember that generally when you write your rate law, if you do not know the order and the rate constant, you write it like this. Right? This is the way you write it. Okay? This is the rate. This is also the negative DCA dt, which is the slope of our line. So it says that you are to plot the LN of CA versus the LN of RA. I would just focus in here. If you take the LN of both sides of this, you will have the LN negative RA equal to the LN of K plus N LN of CA. It's supposed to be written here, but by virtue of properties of the LN, you can place it before the LN. Now, this one is your X. This one is your M. This one is your Y-intercept. And this one is your Y. So that's the reason why it's stated there that you plot the LN of CA. So the LN of CA will be your Y. You plot this and this. The best fit line should give you right away the slope of the best fit line, that is. The y-intercept will not yet give you directly the k, but from that particular y-intercept, you'll be able to get the rate constant. Actually, I like differential analysis method because it's direct. As long as I have my Excel or as long as I have my calculators, I can do linear regression. I'll just get the LN first of my rates, which are the slopes of the lines, as I've discussed a while ago. Then I get the LN of my CAs. Then I can get already the slope of my best fit line. Automatically, the slope gives me the N. And if I get the y-intercept from my linear regression, from that, I can get the value of the rate constant. So there's no more guessing and testing in this case. All I have to do is treat the entire data that is given to me. However, it is partly shall I say, crude because I need to draw my curve by hand. If you have a software that can draw the curve perfectly without passing to all the data points, it's just like a best fit curve on all uh, after you have placed all your data points, then so much the better because that's your best uh, representation, the best by eye drawing of your curve. Then you just select data points from your curve and determine the slope. You have the software again, from that particular point in your curve, you can get the slope of the tangential line. That slope will already be this one. Then you just get the ln that and get the ln of the CA of the chosen point, and that's it. It gives you already the order and the intercept or the rate constant from the y-intercept of your reaction. Okay? Do you have any questions? Okay, I think there's none. I've eaten your time already. I'll just check the attendance. Do I have already, was not able to see, wait. I show, okay, I have already Cynthia, Fritz, and Jelaine. Are you here, Jelaine? Si Manning?
Yes, Miss.
Kainaway ka pa pag-check. Sige, class. I will see you again tomorrow. We'll hear each other again tomorrow on variable volume batch reactor data analysis. Okay? Bye for now. Okay, we'll hear from each other again tomorrow.